Now, another interesting thing to do is, if we go back to our plot of gamma versus beta, most of everyday objects have speeds which are much smaller than the speed of light. Okay, the speed of light is incredibly large. It's 3 times 10 to the 8 meters per second. But if you take, for example, let's say someone walking down the road, maybe you're covering a typical distance of a meter every second or so. So it's many, many, many orders of magnitude smaller than the speed of light. Okay, even if you take a jet plane and see how fast that travels, or even the speed of sound in air, right? Those speeds are very small. The speed of sound in air is 330 meters per second, or if you approximate that as about 300 meters per second, that's still 1,000,000 times smaller than the speed of light. Okay, so for almost all everyday objects, the speeds that we're looking at live down here. Everyday objects have speeds which are over here. And we'd like to understand what happens to this dictionary in the limit of those small speeds. Okay, what we would expect is that you should just get back the dictionary of Galilean relativity at small speeds, because that's something that that is intuitive to us, and we see works to a very good approximation for our everyday life. Okay, for everyday speeds. So another interesting thing to do will be to ask, what happens to Lorentz transformations, or this dictionary of special relativity, in the limit v much, much less than c, or equivalently in the limit where of everyday speeds, okay, speeds that we're familiar with on a daily basis. So first, let's look at the equation for x prime. So x prime, which is the coordinates of the moving observer relative to a frame S, would look like this. It's 1 over square root of 1 minus v squared by c squared into x minus vt. Okay, so in the limit that v is much, much less than c, x prime is approximately x minus vt. So this is very good, because it tells us that we recover one of the transformations of Galilean relativity, which is that the position as measured by the moving observer would just be related to the position as seen by the original observer minus vt. Okay, but now we also know that time is relative. Okay, that is, the time t prime as measured by the second observer is not going to be the same as the time t as measured by the first observer. So how do we, what happens to the relativity of time in the limit that the speeds are much smaller than the speed of light? So for this, let's look at the relationship of t prime to t. So t prime is 1 over the square root of 1 minus v squared by c squared into into t minus vx over c squared and x prime is, we'll just write this out, is 1 over 1 minus v squared by c squared times x minus vt. Now, when we talk about time, we have to be a little careful. We should talk about a specific clock, that is a clock moving with a specific observer in the frame S prime. So let's take the observer in the frame S prime who is moving with a speed, who is located at the position x prime is equal to 0. Okay, let's take a specific observer in frame s prime, and we will ask what is t prime for this observer. Okay. So for this observer, what we would have to do is we'd have to invert these relationships. So first let's invert those relationships. So we can write, and we already saw that the inversion just means that we replace v by minus v. So we would just write t and x as t plus, or t prime plus v x prime over c squared. And now, since we're fixing the observer x to be at x prime is equal to 0, okay, that gives us t is 1 over square root of 1 minus v squared by c squared t prime. This is an exact relationship. However, if we go to the limit that v is much, much less than c, then that gives us t is equal to t prime in the limit v much, much less than c. So time ticks at the same rate for both observers in the limit of everyday objects where speeds are much less than the speed of light. And the relativity dictionary just boils down to the Galilean relativity dictionary. Okay, in the limit that the speed is much, much less than the speed of light. So let's summarize some of the key features that we've learned of Lorentz transformations. Lorentz transformations. One is relative speed v. Okay, I'm allowing it to be positive or negative, but the magnitude of it should be less than c. Okay, if you want a valid dictionary, which means two inertial frames s and s prime, or the frame s prime as seen in the frame s, can only be moving at a speed smaller than the speed of light. That's the only case where this dictionary is valid. Second, if I want to go from frame s to frame s prime, I use a velocity transformation parameter v. Then the inverse transformation to go from s prime to s just uses minus v. Okay, so this is about the inverse transformation. And finally, we saw that in the limit that the speeds v by c is much, much less than 1, okay, or that is for small beta or equivalently small eta, we saw that we get back Galilean transformations. Which is why the ideas of special relativity did not really come about until we began to study light or things moving close to the speed of light.